Okay, so let's talk about the conditions under which we can use p theta st in place of p theta prime of st and still have a reasonable objective that accurately approximates the return of the new policy. So to recap, what we want to do is we want to ignore the distribution mismatch. We want to use p theta of st instead of p theta prime of st, such that the only dependence on theta prime in this whole equation is in the importance weight. Because we know from our previous policy gradient lecture that if we differentiate the thing on the right-hand side, we get exactly the policy gradient. So we want this to be true so that j theta prime minus j theta is well approximated by a bar theta prime, this thing on the right-hand side, so that we could just maximize a bar and get a better new policy. And what we're going to try to show is that p theta of st is close to p theta prime of st when pi theta is close to pi theta prime. And when that's the case, then the right-hand side approximates the left-hand side, meaning that the difference between them can be bounded by some quantity which is small if the difference between pi theta and pi theta prime is small. Okay, so this is what we're interested in. We want to show that pi theta st is close to pi theta prime st, p theta st is close to p theta prime st when pi theta is close to pi theta prime. So let's start with a simple case. Let's first assume that pi theta is a deterministic policy, which means that we can express it as at equals pi theta of st. We'll generalize this to stochastic policies later, but I think the deterministic derivation provides a little bit of intuition, which then makes the stochastic case easier to understand. So in this case, what we're going to try to show is that the state marginals for theta and theta prime are close if pi theta prime is close to pi theta. Now, pi theta prime is not necessarily deterministic, and the way that we define close is that the probability that pi theta prime assigns to any action that is not the action that pi theta would have taken is less than or equal to epsilon. Essentially, there's a bounded probability that pi theta prime does something different. So if this is the case, then we can write the state marginal at time step t for theta prime as the sum of two terms. The first term describes the case where every single time step up to t, the new policy pi theta prime did exactly the same thing as pi theta. And since the probability of doing exactly the same thing is 1 minus epsilon, this term has a multiplier of 1 minus epsilon to the power t in front of it, and the state marginal is exactly p theta st, because if you did all the same things as pi theta, you have the same state distribution. The other term is simply everything else. It's 1 minus epsilon to the t, and it multiplies some other state distribution, which we're going to assume that we don't know anything about. So we're going to call it p mistake. This is the distribution over states you get if you made at least one mistake, and we're going to assume that we don't know anything about it. So it could be like that tightrope walker from the imitation learning lecture at the beginning of class, where if you fall off the tightrope, you can never recover and you're in some completely different place. So, of course, most of you hopefully recognize this equation as being exactly the same as the equation we had before when we analyzed behavioral cloning. And in fact, our assumption is very similar to the assumption we had before, which is that the new policy has a bounded probability of deviating from the old policy. So this is the probability we made no mistake, and this is some other distribution on which we're going to make no assumption whatsoever. So hopefully this seems familiar to all of you. And just like before, this equation implies that we can write the total variation divergence between p theta prime and p theta as essentially just the part that's different, right? So that 1 minus epsilon to the t times p theta st part has 0 total variation divergence against p theta of st. So it's only that second part. And that second part has a multiplier of 1 minus epsilon to the t in front of it. And that multiplies the TV divergence between p mistake and p theta. Now, we can't bound this TV divergence to p mistake minus p theta because we're making no assumption on p mistake. So the only bound we have is the trivial bound, which is that any total variation divergence always has to be less than or equal to 2. So that means that the total variation divergence between the state marginals is bounded by 2 times 1 minus epsilon to the t. This is all exactly the same as in the imitation learning analysis that we had in the second lecture. And we use the same useful identity, which is that 1 minus epsilon to the t is greater than or equal to 1 minus epsilon times t for any epsilon between 0 and 1, and that allows us to express this bound as a quantity that is linear in epsilon and linear in t. So the difference between the state marginals is less than or equal to 2 times epsilon times t. Okay, so it's not a great bound, but it is a bound because it shows that as epsilon decreases, the state marginals become similar to one another. But of course, this was all for the case of the deterministic policy pi theta. In general, pi theta will not be deterministic. So what we're going to do next is we're going to analyze the general case where pi theta is an arbitrary distribution, and this proof follows the proof in the trust region policy optimization paper, which is referenced at the bottom of this slide. Okay, so here we're going to say that pi theta prime is close to pi theta if their total variation divergence is bounded by epsilon for all states st. Now it turns out that we actually don't need the bound to be pointwise. It turns out we can actually use a bound that's in expectation, but let's go with a pointwise bound for now because it's a little easier to explain. But keep in mind this will also hold true if the bound is in expectation, meaning the expected value of the total variation divergence is less than or equal to epsilon. Okay, so a useful lemma that we're going to use for this analysis is this one. This lemma will take a little bit of unpacking, and I'm not going to prove it. This is in prior work, but it's referenced in the trust region policy optimization paper at the bottom. So this lemma says that if you have two distributions, which I'm going to call px and py, and the total variation divergence between these two distributions, meaning the sum over all values of x of the absolute value of the difference between px of x and py of x, is equal to epsilon, so the total variation divergence between them is epsilon, then there exists a joint distribution, px comma y, so that its marginal p of x is px of x, and its marginal p of y is py of y, and the probability of x equals y is 1 minus epsilon. So to unpack this lemma a little bit, what this says is that if you have two distributions over the same variable, px of x and py of x, and their total variation divergence is epsilon, then you can construct a joint distribution over two variables such that the marginals of that joint distribution with respect to its first and second argument are the two distributions you started with, and the probability of its two arguments being equal is 1 minus epsilon. And intuitively, the reason that this lemma is useful to us is that we essentially want a generalization of the assumption from the previous slide. So in the previous slide, our assumption was that there's a 1 minus epsilon probability that pi theta prime takes the same action as pi theta. So if we could express a probability that pi theta prime and pi theta will take the same action when both of them are stochastic, then we can use that to generalize the result from the previous slide to the case where the policies are stochastic. So essentially this says that px of x agrees with py of y with probability epsilon. And that means that pi theta prime takes a different action from pi theta with probability at most epsilon. In retrospect, this is actually kind of obvious because if their total variation divergence is epsilon and total variation divergence is the difference in probabilities, it kind of makes sense that the sliver of probability mass that is different between them would have a volume of epsilon. So if you kind of have a more geometric way of thinking about it, just imagine the two distributions as bar graphs, overlay them on top of each other, and look at the differences in the bars. The volume of those differences will be equal to epsilon, which means that your probability of doing something different is epsilon. So that's kind of the geometric intuition. But if you prefer to think about things symbolically, then hopefully this lemma kind of puts your mind at ease. That, in fact, if the total variation divergence is epsilon, then the probability of a mistake is at most epsilon. So what this lemma allows us to do is it allows us to state the same result that we had on the previous slide, which is the total variation divergence between the state marginals is 1 minus epsilon to the t times p mistake minus p theta, only now we can say this even when pi theta is stochastic, provided the total variation divergence between pi theta prime and pi theta is bounded by epsilon. So from here, everything is exactly the same. We can write the same bound, and we can say that the state marginals differ by at most 2 times epsilon t. Okay, so essentially the trick that we used on this slide was to use this lemma to express a probability that two policies will take different actions in terms of their total variation divergence. Okay, so this is the result that we have on the state marginals. So what does this tell us about the actual objective value, right? What we want is we actually want to relate the two objectives expressed in terms of advantage values. Well, so for this I'm going to derive another little calculation which describes the expected values of functions under distributions when the total variation divergence between those distributions is bounded. So we're going to have some function f of st, which in our case is this complicated thing that involves expectations over actions and advantage values. But it doesn't really matter what it is. Whatever it is, let's call it f of st. We can bound its expected value between the two distributions. So we can write the expected value under p theta prime of st of f of st as the sum over all possible states of p theta prime times f. And we know that this quantity is greater than or equal to the sum over all the states of p theta times f minus the total variation divergence between p theta and p theta prime times the maximum value that f could possibly take on. So the way that I arrive at this calculation is I write p theta prime as being equal to p theta prime plus p theta minus p theta. I group the terms to get a p theta times f minus a p theta minus p theta prime times f. And while I don't know the absolute value of the difference in the probabilities, I only bound the total variation divergence. If I multiply them by the largest value that f takes, I'm being as pessimistic as possible. So that's what allows me to write this inequality. If this is not clear to you, then I would recommend pausing the lecture now, getting out a piece of paper, and actually deriving this inequality yourself. It's a good exercise to do to make sure that you understand how to manipulate total variation divergences. So if this inequality doesn't make sense, please get out a piece of paper, try to work through it now. So pause the lecture and do that. And if you're having trouble doing that, then please ask a question in the comments, and we'll go over this in more detail in class. Okay, so then all we do is we take that first term, and we notice that it's just the definition of the expected value under p theta, and we take the second term, and we replace it by our bound on the total variation divergence, which means that the expected value under p theta prime of f is bounded below by its expected value under p theta minus an error term, which is 2 times epsilon times t times the largest value that f can take on. Now this error term might seem pretty big because, the largest value of f might be huge, but remember that everything is multiplied by epsilon. So as the two policies get closer together, as epsilon gets small, that second term can always be made arbitrarily small so long as f is bounded, basically, so long as f doesn't go off to infinity for any state. So this was the equation that we were originally concerned about. We were concerned about the expected value under p theta prime of st of the expected value over the actions of the importance sampled estimator for the advantage. So by taking everything inside the brackets to be f, then we can bound this quantity below by the expected value under p theta of st of the same quantity. And this thing now just looks exactly like the thing that we differentiate to get the policy gradient, minus an error term, and the error term is 2 times epsilon times t times a constant c, and the constant c is the largest value that the thing inside the brackets, the thing inside the state expectation, can take on. Take a moment to think about what the largest possible value for that quantity inside the brackets could be. Basically, what should we use for c? The thing inside the brackets is a really complicated equation, but notice that most of the terms in that equation are probabilities. And we know that probabilities have to sum to 1. So, in fact, what we can notice is that the quantity inside the bracket is basically, it's some expected value of an advantage. And what is an advantage? Well, an advantage is the sum of rewards over time. So that means that the largest value that C could take on is the largest possible reward times the number of time steps. Because all those importance weights and all those expectations, they have to sum up to 1. So that means that basically the expected value of any function can't possibly be larger than the largest value that function takes on. And the largest value that an advantage can take on is the number of time steps times the largest reward. Because ultimately an advantage is the sum of rewards over time. So that means that the C is on the order of the number of time steps times R max. And if you have infinite time steps but you use a discount, then you know that the discount values, they form a geometric series, so they have to sum to 1 over 1 minus gamma. So in a finite horizon case, C is capital T times R max. In an infinite horizon case, it's R max over 1 minus gamma. By the way, as an aside here, if you're doing reinforcement learning theory and you ever see a term that looks like 1 over 1 minus gamma, just mentally substitute the time horizon for that, because 1 over 1 minus gamma is essentially the equivalent of a horizon in the infinite horizon case. It's basically the number of time steps, the effective number of time steps that you're summing rewards over. Okay, so essentially all this says is that maximizing this equation at the bottom maximizes a bound on the thing that we really want, which is the expectation under p theta prime, which we've proven to be the same as maximizing the RL objective. And the thing that we have to watch out for is that we get this error term that scales as 2 epsilon t times a constant. Everything in that error term is a constant except for epsilon, and epsilon is the total variation divergence between your new policy and your old policy. So take a moment at this point to think about what kind of RL algorithm we should use informed by this derivation. Basically, this derivation suggests that a certain very tractable objective is a good approximation to the true RL objective under certain circumstances. And this implies something about the sort of reinforcement learning algorithm that we should be using if we want to get good performance. All right, so what we have so far is that maximizing this objective, basically the expected value under p theta, the expected value under pi theta of the importance weighted advantage, is a good way to maximize the RL objective so long as pi theta prime is close to pi theta in terms of total variation divergence. Essentially, if you restrict theta prime to not go too far from theta so that this constraint is satisfied, then maximizing this tractable objective is the same as maximizing the true RL objective. How do we maximize this objective? Well, we take its derivative with respect to theta prime, and theta prime only appears in the importance weight, so when we take its derivative, we get exactly the policy gradient. So our derivation, what it has shown so far is that this is a good thing to do if theta prime stays close to theta. So for small enough epsilon, this is guaranteed to improve j theta prime minus j theta, which means that it's guaranteed to improve the RL objective. Okay, so in the next part of the lecture, we'll talk about how to actually do this in practice.